this Institute for Theoretical Physics. It's a really nice place, and traditionally it's a place where people did lots of work on high energy physics, right? And this situation changed somehow when Alexandre, our current director, came. But it's really a delight to see so many people interested in soft matter today, and we have an audience of almost 100 people here. And no one better than Professor Hartmut Löwen to give the colloquium today. Professor Löwen did his PhD in Dortmund, then he went to Munich as a postdoc, and then to Lyon, Munich again, and was hired as a professor at the university. Heine, you apologize me for my pronunciation, German pronunciation.
It's okay, it's good.
University in Düsseldorf. He was one of the people, you know, there has been lots of work done on this field of physics called active matter, and he's one of the few people who has actually shaped the field, I would say. I'm not exaggerating, in his very prolific career. So it's really a pleasure to have you here, and welcome, and the floor is yours.
Yeah, thank you. Thank you very much, Danilo. This was a very nice introduction, and I'm happy to be honored to give a colloquium here in front of a general audience. So I will try to be also general, yeah, a little bit about high energy physics, but only as a side remark. So my topic are self-propelled particles or active matter, and also the point of view of physics for these non-equilibrium systems. As Danilo explains, I am from the Heinrich Heine University in Germany. Heinrich Heine is a poet who was born in Düsseldorf, but hated Düsseldorf and lived in Paris for the rest of his time. Here is our university campus. This is the city of Düsseldorf. Here's some third-party funding. Maybe some of you know the Humboldt Foundation. It gives money for postdocs and also for senior people to come to Germany. And I will structure my talk with an introduction and then discuss active Brownian motion, motility-induced phase separation, then inertial effects, and if there is time, some collective effects of inertia. Please interrupt me if anything is unclear. I'm happy to answer any questions, also during the talk. This is in Africa. This is an impala antelope, yeah? And for some reason it ended up on an island, surrounded by water. And what you can also see here is a croc. Now you can imagine what the croc wants to do, and that is in this movie. The impala decides for some reason to escape, jumping in the sea, getting to the river, to the side here, and the croc is following. And now I stopped the movie here since there's a bloody end. It's a matter of swimming. Yeah? It's a matter of swimming speed. Who will win? You know running, but this talk has more to do with swimming in a liquid. And what happens in the macroscopic world also happens in the, say, micron size, mesoscopic world. Here you see a white blood cell, which is hunting a bacterium. Let's see what the movie tells us here. It cannot see it, it has no eyes, but it can smell. There's so-called chemicals which are smelled. And then here it's swallowed, indeed, the bacterium. And that's its prey, so it's a predator-prey situation. Much, much smaller length scale than here. So now I come to a famous statement of Feynman, which he did a long time ago. There is plenty of space, of room at the bottom, where he introduced nanoscience. By the way, the Nobel Prize of Chemistry was given today to nanodots, no? So it's a very actual thing. He said, well, I will not quote this, but he said, well, I have an idea. I don't want to go to the doctor any longer. If you have cancer or another serious disease, no operation, nothing. I just swallow a tablet. And in this tablet, there are little robots, and they go on their own, look in your body for the dangerous cells, and kill them. They take a little knife and slices it out. Other small machines might be permanently incorporated in the body to assist some inadequately functioning organ. Now comes the interesting question, how do we make such a tiny mechanism? I leave that to you. And I would say, well, we are not yet there, but we are on a very good track now. So this is a motivation to study little micron-size swimmers, micro-swimmers, which find their way in your body, so in a complicated environment. And that's a new branch of physics. So it's a bit counterintuitive, but what you know from the macroscopic world, so here is a human being swimming, high speed. It swims about 1.5 times the body length. And if you think that is a fair comparison, go to, say, micro world here. This is 2 micrometers, and this is a bacterium that propels. It swims much, much faster, not in absolute speed, but if you relate it to its body length, it swims 100 times faster, almost. It's 100 times than the body length in 1 second. So how do they do this? There is an important number in fluid mechanics or in hydrodynamics. This number is called the Reynolds number. It's a dimensionless number which measures more or less inertial effects. Yeah? If you do a breaststroke, yeah, and you keep like this, you are attracted by the flow. But there's also friction. So this Reynolds number relates the inertia of your body with the friction of the water. And the problem here is there's only friction. It is completely overdamped. There is no inertia here. If you look how this Reynolds number scales, it is almost 0. While here it is much larger, and of course for a racing car, even larger. So at such small Reynolds numbers, so in the very viscous regime, everything is friction. Friction, friction. So highly viscous thing. It is as if you would swim in honey. Try to swim in honey. Very viscous surrounding. Huh? There is a so-called scallop theorem, which is the following. How can you propel? How can you move forward? Is it possible to move forward just by a scallop motion, which opens its mouth, closes, then it goes? And then does the next step open and close. This is not what happens. When a scallop is opening, it goes like this. If it's closing, it goes back or the other way around. So an important theorem is you need a non-reciprocal path in time. So if you can just mirror in time your trajectory, you will just go back and forth. You will not self-propel. This is completely different for high Reynolds numbers. And this is the reason why many of these, say, microbes and bacteria self-propel via a corkscrew helix. So they are rotating. And you know, if you're rotating this way and you are anti-rotating this way, this is not time inversion symmetric. This is different. Clockwise, anti-clockwise makes a difference. And that's why they can move, and that's why they do move. Okay. So the new development in the last decade or the last decades, and the first paper in this business is now almost 20 years ago, is you do not use mechanical motion of limbs for self-propulsion. You don't do this what the impala antelope does, yeah? And the croc does this, but you do it without mechanical motion. How? You take a micro or nanoparticle and let it self-generate a gradient of something. For example, it's spitting out a chemical. It creates around its surrounding a gradient of something. Can be also temperature. And then, you know, in a gradient, a particle moves. But the particle carries this gradient with it. So it moves and moves and moves. And that is like a motor. It's a self-propulsion. It's not that you hammer from the outside on the particle, but the particle, say, creates this on its own. And that's the new development. And these are artificial model microswimmers. They are not living, yeah? They're just dead, but there is a mechanism which gives them a motor, an autonomous locomotion. And there is, I think, an important paper by Ayushman from Pennsylvania, now almost 20 years ago, where they put a Janus particle into reactive solvent. I will discuss another mechanism now. So most of the mechanisms work with a Janus particle. So this is a colloidal particle, say a plastic ball, but a plastic ball at very small length scale, a micrometer. You can hardly see it. You cannot see it with your eye. But it is coated, a hemisphere, half of it is coated with another material than the other half. It's like the Roman god Janus, who had two faces. Yeah? This is a Janus particle. You can prepare these particles now very cheaply. And now you put them into something to self-generate a gradient. Here is a catalytically driven situation. So here you have gold and platinum side. You put it into not only in water, but into a water H2O2 mixture. So H2O2 is a reactive sink, which makes your hairs white. Yeah? And it decomposes into oxygen and water after a certain time. Now, this chemical reaction here is catalyzed here, but not here, which means here is much more going on. The oxygen bubbles, and then this little cigar Janus particle gets into motion, like a little submarine. Yeah? It goes through the water. And that is, I mean, here, this is one of the first papers by Paxton having realized this. There's one little problem here. You are running out of fuel. There is, after a couple of hours, there's no H2O2 available, and so the fuel is taken away, and then the particle stops, and then it's randomly kicked like a normal Brownian motion. There is a help out of the fuel limitation, and this is an ingenious idea by Clemens Bechinger in Konstanz now in Germany. He used continuous laser illumination for Janus particles. And I will explain now a little bit the mechanism behind it. The mechanism works with a fluid-fluid demixing, so with a phase separation of the solvent. So now you put the particle not in a water H2O2 solution, but in a binary mixture of water and lutidine. Lutidine is a very nasty material. It stinks a lot, but it has the advantage, if you mix it with water, that you get a lower critical point here. So this is a bulk phase diagram of a water-lutidine mixture. If you remember your thermodynamics phase diagrams, here's temperature. This is relative lutidine concentration in percent, so relative to the full solution. And at about, say, room temperature, so 33 degrees, and about, say, a volume percent of 30, there is a critical point. This is a real critical point. And if you are below the critical point in A, you have a one-phase fluid. Yeah? And if you are at higher temperature here in B, the system would spontaneously decompose into lutidine low and lutidine rich fluids. So far, so good. Now you put such a Janus particle in this mixture and you use a laser illumination. Not so much, a little bit of intensity, which makes it, at the metallic part here, a little bit hotter than here. And then, that means here's local demixing. And now there's an instability. So if you kick this particle with an initial kick, then you have to establish or replenish this region with lutidine. It's lutidine rich. So this says, give me lutidine, give me lutidine. The lutidine has to flow from the outside to this region. This creates a solvent flow. Yeah? And then there is momentum conservation, or the particle exposed to this solvent flow, and it will flow with the solvent. And this makes it self-propelling. It really works. Yeah? And the good news is, you can steer the self-propulsion speed, so the speed of the impala, yeah, by laser illumination. No laser light, the particle stops. Large laser light, it goes quickly. Laser light small, okay, smaller speed. Laser light on and off, it's like run and tumble, so you go, you stop, you go. You can do landscapes in laser light intensity, it's fantastic. And even though, but this is a bit more complicated, I will not go into the details, it's very high laser intensity. So if you do a lot of laser light, the particle will go not to the left but to the right. So you can even inverse the sign of the self-propulsion externally. So everything is under control. This is nice. Here is a gauge curve. It's applied laser intensity. Here's the resulting self-propulsion speed. You need a certain threshold here, and then it's almost linear. And for high laser intensity, it goes down again, even to the negative. Fine. This is a review, which was basically organized by Giovanni Volpe. These are the Volpe brothers. They are not twins. In this Review of Modern Physics paper, a review on active matter. And here is a figure which shows different self-propelled objects from the biological, the living world, and the artificial swimmers. Size is here on the log scale. Here is the resulting speed. And we are almost where the biological, say, the swimming bacteria are in terms of speed. Now, physics. What is the simplest thing to describe self-propelled motion? I mean, you all know the Ising model. I say Ising and not Ising, since Ising was German. Yeah? Ising was born in Cologne, which is not so far from Düsseldorf. The Ising model, so a very simple model which has most of the features in it, so which is, say, the genuine model for self-propulsion. And this is one possibility, there are others, but one basic possibility is active Brownian motion. So I would like to keep fluctuations. They are very important on the micron scale. Yeah? So even without self-propulsion, you have Brownian motion. So this gives you stochastic equations. I cannot avoid that. And a mechanism to self-propel in a liquid, but at very low Reynolds number, so completely overdamped. And then you can write down these two simple equations. This is a force balance. Normally, you know you have mr double dot plus a damping. This you know from your mechanics of a damped harmonic oscillator, right? Here there's no inertia, it's just overdamped. And here you put all the other forces. All the other forces are fluctuating forces. I take them as Gaussian white noise. Zero mean, second moment is related to some kind of noise strength, which I call effective temperature. For the experts, a dangerous concept, since we are not in equilibrium in general, but I call it noise strength or effective temperature. It doesn't matter with the real temperature. And then here is a self-propulsion force. This force makes a particle in the absence of noise moving with a speed v0 along an orientation vector. And this makes it a bit more complicated. It's not only the center of mass, but also the orientation of the Janus cap, which we take into account. And so this is a swim force or a self-propulsion force, or better, an effective self-propulsion velocity. I ignore all the details, yeah, of wetting or limb motion. I just put it in one effective parameter, which is v0. But it's along this direction. So you have, like this rod, you have an orientation, Janus cap, and then you go along the orientation. With a constant speed, is nothing else is happening. But then there is noise. There's dangerous noise. So there's an equation of motion for the orientation. Yeah? And the orientation is in 2 dimensions, cosine sine of an angle phi, so relatively easy. So you have an angular speed, which is also overdamped. So we have a rotational friction coefficient here. Yeah? And here's a torque. And I take the torque just also to be a Gaussian random number. So white noise for the torque, no memory here. And then you have 2 coupled equations, which you can try to solve. And that's active Brownian motion. Yeah? So if you say, we neglect this is an important term. The red term is important. We neglect this, we said V0 is 0. We are back, so first of all, the 2 equations decouple. You can solve them independently. And we are back to Einstein's famous paper on Brownian motion. This gives you Brownian motion. Now, you know what a random walk is, that is Einstein. What you have here is, say, a force, and this force is along the orientation, and the orientation has also noise. But you are going with a constant speed v0. This is not a random walk. So a random walk would be if I go randomly left and right. That's what a random walk is. But here I go with a velocity v0, and I have noise on top of it. So it's like a random drive. Yeah? This is a term which was used by Thomas Frano. So random drive is I go, maybe one back, and then I go again. But in general, I'm drifting. That's what it is. And you can say, well, it's like a car which goes at very high speed, V naught, yeah, it's self-propelling, but there are fluctuations. There are fluctuations of the whole car, that are the translational fluctuations in all directions. These are the easy ones, but they are dangerous fluctuations. These are the fluctuations of the steering wheel. If you go the highway, very high speed, on the little fluctuations of the steering wheel, it makes huge impact. Yeah? So that's the problem here. So think you have a blind driver, it's politically not correct, but who goes with very high speed and then does wide fluctuations of the steering wheel. That's a typical trajectory of a random drive, or some people call it a persistent random walk. And then you can say, what is the statistics? What is, say, the mean displacement? The mean displacement is 0, since you can, with any probability, you go in any direction. By symmetry, this is 0. But if you square the displacement, so this is where the particle was at a time 0. This is where it is after a time t, after a lag time. You square this, and then you average over the noise, you get something that is non-trivial. And if there is no noise, there's a ballistic trajectory, which means immediately that this scales as t to the power of 2. So t to the power of 2 is a ballistic scaling regime. It just means that you go with a constant speed. And you can, for this active Brownian model, you can really calculate the MSD. It's something you can do as an exercise. And it is in this paper by Golestanian and Hause. And you get this result. So this is a standard diffusion for the translation. Not so interesting, that is Einstein. But then you get something here. And if you expand it, yeah, expand it for small t, you see for small t there is nothing. Since you cancel the first two terms, this term is winning. So for very small t, short time, you have a diffusion coefficient that is the translational short time diffusion coefficient. Now for very long time, you see this is also linear in t. This gives an additional term to the long time diffusion that is v squared, v naught squared over d rod. Yeah, this is not important. So since v naught is normally large, the diffusion coefficient scales with v naught squared. This is a lot. So it means you go with your car and explore a big region at very high speed. And if you expand this to second order, you get a term that is proportional to t squared. So you have, if you do a log-log plot of the MSD, the mean squared displacement, you have a diffusive part where everything is linear in time for short time, so very long times, again diffusive, but with another diffusion coefficient, with another prefactor in between, a ballistic, which goes roughly as v naught squared, t squared. So far, so good. Are there any questions? Since we're getting now into the, say, more complicated collective phenomena. Okay. This was one single particle. And then there is hope to do something analytically. Now I go to many particles. Many particles, so I is now a particle index. I write down equations of motion for many particles. I runs from 1 to n. Every particle has an orientation, every particle has a position, and I write down the same equations except for this term, which is an interaction force. I assume now, very important, that there is a pairwise interaction here, which only depends on the distance between two particles. It does not depend on orientation. No, it's different for flocking systems where they normally orient. It's the simplest thing. They just bump into each other and see each other normally by repulsive interactions. We took here, but this is not important, a repulsive short-range potential, according to Weeks, Chandler, and Anderson. And then here's an important parameter which measures, say, the strength of the self-propulsion relative to the thermal noise. This is the so-called Peckley number. If Peckley is 0, there's no activity. If Peckley is very large, there's a lot of activity, much more than fluctuations. And what you get here is a new effect that is called motility-induced phase separation. It's nowadays called MIPS, motility-induced phase separation. Why is this interesting? Okay, you know that many systems, like water, also rare gases, argon, have a gas phase and a solid phase, but also a liquid phase. And van der Waals in his PhD thesis proved that the liquid phase has to do with attractions. By the way, van der Waals didn't receive the best cum laude mark in Amsterdam in these days, since nobody understood his thesis, but he says, well, and you know this van der Waals theory, no? For the phase diagram. Here, there are no attractions. It's repulsive. But nevertheless, there's fluid-fluid phase separation, which comes from the activity. This is something which is maybe astonishing. What is the picture behind it? What is the mechanism of this clustering? I give you a very simple picture, which is, if you do it in a more quantitative way, the correct one. So suppose you have repulsive particles. So they are moving with the same speed according to their orientation. And then there is like something like a Mercedes star configuration where three particles opposing each other are meeting. So it's a triplet collision. Maybe it takes a while, but this will. Once you have such a collision, you are in danger, since these particles will just do this forever. Unless noise comes and rotates this particle, rotational noise, yeah, and then it can fly away. This time scale, the time scale upon which this, say, liberation process happens is 1/d, so it's a rotational diffusion time. But once you are in the cluster, there can also neighboring particles are flying to the cluster. Yeah? And if you're in a dense system, there are many particles, and they block this way of escape, and then the cluster grows. This happens on a time scale, typical particle distance, scales with the density over V0, over the velocity. And if you equate these two times, it's a matter of two time scales. You have already most of the physics of MIPS. This is the underlying reason. Okay, experimental proof. Here are the experiments of Clemens Bechinger, Janus particles in water lutidine. You see little caps here. Yeah? So this is on a substrate. Yeah? You see the particles moving, laser intensity is turned on. So the Peckley is about 40. And you see, well, they are colliding, but they are not really big clusters. They are clusters which are transient, but then they dissolve. And that's what you get in some kind of steady state. But if you increase or double the Peckley number, which is shown here, it's different. You get clusters, but the clusters are growing, also dissolving, but there is, in the very end, a big cluster, which is macroscopically large. And this you can do also in a simulation. This is a simulation of active Brownian particles. The green color means the cluster criterion is fulfilled. These are short-living clusters. This is a big cluster which grows. So this fits more or less on top of each other. So that is in this paper now 10 years ago. Now we come to the more subtle case of a theory for that. Yeah? If you like, van der Waals theory for active systems, or it is, after all, a Cahn-Hilliard theory for phase separation. One way which Thomas Speck did, he was in my lab in these days, you start from the Smoluchowski equation with self-propulsion along the orientations. This is exact in the sense it reflects the active Brownian motion model completely. Then you do a closure which is in non-equilibrium, that is an approximation, and an instability theory and a long wavelength limit, and you end up, and this is surprising, that for very, very long length scales, you can map the dynamics of a system on a Cahn-Hilliard equation. The Cahn-Hilliard equation, maybe you know, it's a paper which has more than 11,000 citations, by the way. So it's a big paper in phase separation kinetics. And it tells you that it's a generalized diffusion equation here. And with a free energy functional, that is a square gradient term, and a free energy that has a double structure. That means, so one immediate consequence is, for very, very long times, so very big clusters, it is Cahn-Hilliard, it's effectively equilibrium. So the growth exponent should be 1/3. We don't have to simulate that. Yeah? It just comes from this mapping. And I should say these approximations are getting asymptotically exact in the long wavelength limit. So there's reasons to believe that that is fine. But for finite times, it's different.
Hartmut, can I ask a quick
Sure,
question?
sure.
Are the clusters crystalline or are they high-density liquids?
Very good point. In the simulation, they are crystalline. Normally, they are crystalline. And in the experiments, they are often high-density fluid. This is fine-tuning, but sometimes they are also crystalline. It depends on the parameters, whether they are crystalline or not. Now, the whole phase diagram has been mapped out, much more precise than this one. And, I mean, the heart of any statistical mechanism goes, there's an ecstatic phase for the active system. And so Werner Kraut and co-workers have figured that out. So it's much more complicated than here, and then it depends whether you have phase separation into gas solid, or into gas liquid, or into gas ecstatic. So it's a very good point. Okay, and now I want to do a little bit a step back to the antelope and the croc. Inertia, inertial active matter. So what we did here is, if you have the size of a swimming object, we went to micrometers, that is 10 to minus 6, and then everything is viscous and there are fluctuations. This is ABP, this is active Brownian motion. Now I would like to go a little bit up again to macroscopic sizes, but still keep fluctuations. Then we have something like active Langevin motion, which has inertia. So there's now an inertia term. Viscous is there, not so dominant, plus fluctuations. And the fluctuations can be everything. Vibration of hoppers, a flying toy balloon. A toy balloon is a very good example. If you blow up the toy balloon and let it fly, it's a self-propelled object that has fluctuations. It's macroscopic, and it has inertia. Here's a very nice review article of Daphne Klotzer, which says different creatures here on different length scales, different Reynolds numbers. What I want to do is very simple. I want to study the dry case. So effectively, there's no solvent. If you do a real solvent, you have to solve the Navier-Stokes equation. It's finite Reynolds number, not easy. So I neglect everything. So I will talk about dry active matter, while Daphne Klotzer is talking about wet active matter. So some people say this is scalar active matter, since only the density is relevant, but that's for the experts. So very simple case. And we know what to do now. We just have to add here inertial terms. We take them back from the harmonic oscillator. It's not overdamped any longer, so I have inertia here. It's mr double dot, and for the rotations, it's a moment of inertia, J, times the angular acceleration, phi double dot. This is the angular acceleration. So these red terms are inertial effects. This is the old picture of Brownian motion. By the way, you can put even a constant torque here. That's another situation where you have chirality. I will not talk about that, but say, if put this constant torque to 0, plus the noises. So it's not any longer a micro swimmer. It doesn't swim in a liquid. It flies in the air. It's like a little insect. And there are realizations in nature and also in artificial systems, and I will talk about that soon. So it's a micro walker. Now there are horribly many timescales which are important. So this is a very busy slide. Forget about the yellow one. This is 0. We have a persistence time. This is the time for the orientations to relax. We have a translational diffusion time. This is not relevant. Forget about this. This is the only time which is relevant for LVPs. It's a dangerous time for the steering wheel fluctuations. But now with inertia, we have 2 additional timescales which measures the ratio between mass and friction. This is for the translation, this is for the rotation. And then you can build 3 ratios which are dimensionless, say calligraphic D0, D1, D2, horrible, but I'm not discussing the details. But what you can calculate now, you can, for a single Langevin flyer, you can calculate the MSD. It's a little bit more complicated, but you get the same expression as Golestanian did for the active Brownian particle. So it's long time diffusion is the translational one, plus V naught squared over 2d rod. And there was a 1 before, but now there's a scaling function, which is G of d naught and d1. It only depends on d naught and d1, so these ratios which I discussed earlier. And the G is a lower incomplete gamma function. So Alexander Sprenger calculated that, and it's analytical, but a bit nasty to evaluate. The important news is, I was expecting a D2 here. No, this scaling function does not depend on the mass. It only depends on the moment of inertia, not on the mass. That's here. Why? Again, what matters is persistence. Again, now we have an inertial car, but for the long-time diffusion, these fluctuations of the steering wheel are much more important than the other ones. So the mass just doesn't contribute to long-time diffusion. And you can compute what this long-time diffusion is as a function of the moment of inertia. It is the old term, and for the low j, it is a linear in j. For large j, it scales as square root of j, and that's it. Why is it monotonic in j? Suppose you increase the moment of inertia, then you are rotationally very inertial. It takes a long time to rotate. In this time, you fly. You fly a long distance. It gives you huge diffusion coefficient. There's a little bit more subtlety for an inertial system. Take this rod. For ABPs, the self-propulsion was along the orientation of the rod in this direction. But now, still, the self-propulsion is along this orientation of the rod, but the velocity of the rod can be different, for example, like this. You have a velocity in this direction and an orientation in another direction. There are two directions. Okay, and now you can correlate those. And we dynamically correlated them. So to say, what is the correlation between the initial orientation at time 0 with the velocity after a time t? Okay, something like this. And I'm motivated by this movie. It's a movie of a racing car. Suppose you are in a racing car, and you want to turn around a corner. It's inertial, the racing car. So if what professional racing car drivers do, first turn the steering wheel, and then the inertia will carry you more away from the corner, and then you go around this corner. So this is what happens. Oops. And I want to quantify this effect now with fluctuations. And therefore, I say, well, what is the probability to find the steering wheel, U is the steering wheel, correlated with the velocity after a time t, and minus, now the difference in the inverse case, where you first have a velocity, and then you look for the steering wheel orientation after a time t. For an ABP, this is 0. For very, very long times, statistically, these two are independent, so the factorized, this is 0. So this inertial delay, we call this function, it's a correlation function, inertial delay function, starts at 0, goes to 0. But in between, in generally, it is not 0. And first, the steering wheel goes, yeah? And then later, the velocity follows. So this term has more weight than this term. So it is positive. And you expect a delay function like that. You can compute it. Alexander did it. There are, again, these gamma functions. And then you can look whether this is actually true for fluctuations. Here's a very simple result in the special case of no moment of inertia, but and no circling. So it's a difference of 2 exponentials. And you see, it is indeed positive. It vanishes if the mass is 0, so that's the active Brownian motion. and the maximum is proportional to V naught. You see this here. This makes all sense. I will not discuss this. There are other inertial effects which are listed up here in papers, and since it is Colloquium, you may consult these references. There is also a Langevin rocket. You know, a rocket works that it ejects matter and then becomes self-propelled, and you can do this with fluctuations. This is a model nobody has explored before. I don't know why, but this is in this paper. Alexander solved it completely. So can we find in nature realizations of active Langevin motion? I think yes. I will list a few of them and discuss them. There are animate examples. Here's a beetle. It's a swimming beetle. It's macroscopic, so it's centimeter size, and it swims normally at the water-air interface. And you can measure, and I got data from Harvey Devereux and Matthew Turner from Warwick for the beetle motion, and you can calculate the delay correlation function. Yeah? You correlate the orientation of the beetle with its actual swimming speed, and you find something similar to that. Marvelous. So there's one example. There's another example even for micron-sized particles. For Janus particles, they're of micrometers. Here's a millimeter scale. These are very little particles, but they are not in a liquid, but in a plasma gas. Then inertia is still important, although these particles are relatively small. They have a mass, they have inertia. And this, you can also illuminate them with light and make self-propelled, say, dusty plasma particles. It's a nice area of research where inertia is very important, and I refer to this paper here, if you want to learn more. Here's a third realization. Let's go to granular systems. We had a talk already on granulates, the post-it particles. Similar idea here, vibrobots. So these are macroscopic particles, centimeter size, and they have little legs. These are plastic animals. We print them from a 3D printer, and we put these normally tilted legs on a vibrating base plate. So there's a base plate that is vibrating, and then you put an animal on it. And I have here another realization, but it's the same mechanism. So these are so-called vibrobots, or hexbots, they're called. They have an internal motor, so you can turn it on. Where is it? No, battery, out of battery. I brought 3 of them to make demonstration possible. Oh, this doesn't work. Why? This one goes. So it has fluctuations, as you can see. It has inertia, and it's the same mechanism. Just the vibration is caused by internally in the particle and not by the external base. But if you would like to get this, you can play around. I give it as a gift. It's difficult to get it through the security control of the airport anyway. So. Okay, so you take such a particle, yeah, and let it run, and then you have these trajectories here. And these are excellent realizations of active Langevin particles. And here is my contribution to a medical application. It's a shitty application. Okay, you really, like Feynman's idea, you take a little pill, this little pill has a vibrobot in it, you swallow it, you digest it, and if you have constipation, this will start to drill, yeah? Making holes and helping you to digest better. Yeah. Okay. So this is really back to the actual experiment which we have in our institute. So this is a movie where such a particle is flying. Okay, sometimes it hits the boundary, then it depends whether you want this. Here's Christian Scholz's hand. Christian Scholz is the master of the experiment. And then we start the process again, and we can average over many trajectories. And here is a trajectory where we colored the orientation, which is marked by the cross here, that is the red arrow, and the velocity, which is the blue arrow. And you can really see, if you look at it first, the red arrow turns, and then the blue one follows. So it's actually a good example for an inertial delayed system that is fluctuating. Here is a delay function. I don't go into the details, so it has this shape within the experimental error. So wonderful. Now you might think, okay, we learned all this MIPS thing, yeah, for interacting active Brownian particles, phase separation. What is going on if you have inertia? So I write down the equations of motion now. This is a repulsive interaction, pairwise, non-aligning. But now you have inertia. And I thought, well, what should come out? It's just a little shift of the phase diagram, and that's it. No. It's more interesting. So first of all, large inertia destroys MIPS. This, I would say, is intuitive. Since if you take this Mercedes star picture of MIPS, yeah, and now you have inertia. Inertia means you bounce back. And this destroys clusters. So the effect is clear that if you include inertia, MIPS will be suppressed. Fine, Haken dahinter. But there's another new effect. You have a coexistence now of two phases. It's a high density and a low density phase, and they have different temperatures. How do you define temperatures? We take the kinetic energy that is positive, and we use the equipartition theorem. It's not valid in equilibrium, but you just take it, yeah, to identify the mean kinetic energy with an effective temperature, and that's it. And the cluster growth exponent is not the Cahn-Hilliard one. It's considerably smaller than 1/3. These are the three results which Suvendhu-Mandal obtained within extensive, say, Langevin dynamics simulations. And I show in this paper, and I show you one movie which is very instructive. So you go, this is a rectangular simulation box with periodic boundary conditions. You see the particles somehow, but what is colored here is not the particle position, but the particle temperature. So this is the temperature. And if you turn it on, the temperature fluctuations, then boom, there's a cool, blue means cool, red means hot, there's a cool area here. And this cool area means very low temperature. Very low temperature also means very high density. It's correlated. How many times? Energy. So we have a velocity, it's inertia, and then we take the kinetic energy, and we say 1 degree of freedom is 1/2 kBt. It's an effective definition. But that's a good point, since you have many possibilities to define temperature in non-equilibrium, but that is what normally people, is one of the options which is close to what you can take. And if you put your finger into a plasma, you feel the kinetic temperature. It is hot if particles have high velocities, so it's not completely away from any perceptions. So recently, Lorenzo Caprini and Davide Brioni, they have performed the experiment on these vibrobots and studied MIPS. And what they found, in fact, they confirmed that the high-density cluster has a different velocity distribution, that is the red one, than particles outside the cluster, that is the blue one. Yeah? So blue is dilute, red is cluster. So unfortunately, blue means now high temperature and red means low temperature. I got this slide just before departing anyway. But it confirms experimentally the theoretical prediction of temperature difference. And now you can think, this is odd. Why is there a temperature difference? Isn't there a heat flow? Okay, you can think about a crazy application. It's a refrigerator which uses the effect that you have this MIPS phase diagram. Now, for the inertial system, you have a coexistence line that goes up. This is the old ABP line. This is a new one with inertia. And it has, if you're close to this, you have situations where the dense phase has a lower Peckley number than the dilute phase. And if you then prepare a motility landscape, which is, say, higher Peckley outside than inside, you can do this, for example, by steering the particle velocities. And then you can create such an area here, which automatically emerges by self-organization as a refrigerator. So you suck in particles, and once you suck in particles, there will be more particles, so you have a refrigerator, there are no walls, everything is done automatically, and then you have a region where you steer a cold region and a hot region. The rest are details. Now I'm coming to the end. And I want to convey another message still. So there was a question about what is the phase in the clusters. They are also active crystals. At high densities, we know we have crystallization. You can also have crystallization of active particles. For example, if you take our vibrods, and at a very high density, they will order on a hexagonal lattice. Olivier Duchot has a very interesting paper here. I think meanwhile it is published in Nature Physics. He has little springs connecting all these vibrobots. So he has a spring, a model spring solid of active particles. And the question is, we know elementary excitations of an active crystal. For example, the vibrations we know from condensed matter physics are phonons. These are the lattice vibrations. What are the lattice vibrations here? Okay, Lorenzo studied that in the harmonic approximation, and the result is, yes, you have phonons, but the lattice vibrations can be uniquely classified. They are either phonons, and then they are identical to the equilibrium phonons, or they are other vibrations which are completely responsible for entropy production. Now we are, an active crystal is not in equilibrium, so there must be entropy production, second law. And these lattice vibrations carry alone the entropy production. And we call them entropons, like phonons. These are elementary vibrational excitations for active crystals which are responsible for entropy production. So here's a standard picture. You have a solid, maybe a solid of Janus particles. You have collective excitations, which are phonons in a thermal bath. Everything is in equilibrium. And if you turn on activity, you have this active force, you get a new kind of entropons. And you can really analytically calculate the spectral decomposition of all these vibrations and cleanly separate them into the old phonons and the new entropons. And you can imagine that I'm not dreaming to find an experiment for these entropons. Are they also in active glasses and so on and so on? This entropon paper is published here. After a long fight with referees, by the way, but we ended up in JCP. Not too bad. Hmm?
Oh, sorry. You measure these entropons. I mean, it's the first time I hear about it. So,
that's a good point.
How do you measure these entropons?
It's a good point, and it's a very important question. So you have to know a lot of information about the crystal, and then you have to correlate the force, the self-propulsion force, with the velocity. Is F dot V. That is the power you dissipate. And that's the key to get the entropon spectra. So you really have to not only see the particles, you also have to know the forces. And therefore it's not so easy. The self-propulsion forces. They are the crucial term for the entropons. So it's hidden in a correlation function. And, but you cannot just make a photo and say, here they are. Since you cannot make a photo to see entropy. Yeah. And now it depends on the mercy of the chairman, whether I get another minute or not. This clock is the measure for, okay. One last crazy idea is once you have this actual active matter systems running, Christian had a paper here where he said, well, I now take spinners. So I take many, many spinners which are rotating by tilted legs, and anti-spinners. And I mix them, and what this, if you wait a long time, what these spinners do, they phase separate. So there's demixing. Here's the clockwise spinners, they like each other, and the anti-clockwise spinners, they don't. They also like each other, but there's an interface. They have to build an interface somehow in this container. But that's an interface which is relatively sharp, so there is demixing. And now when Christian came to me and said, well, what can we do? I said, well, what can you prepare surfactant chains? So these are active surfactants, you know, amphiphiles on the granular scale. So take a clockwise spinner and an anti-clockwise spinner, and then I put them together by a linkage, for example, by a strong spring. I make a pair of rotator, anti-rotator. And then, indeed, if you throw these guys into the solution, they exactly go to the interface, since there they are happy, yeah? Like a normal amphiphile molecule, surfactant molecule. And then they destroy also the interface, and that is what you do if you wash your hands with soap. Huh? Soap is amplified, and it goes between the dirt and your skin and reduces the interfacial tension. And these are so active, say, surfactants, which have not only go to the interface, but they also have a dynamical function. Once they are at the interface, they run along the interface, since they are self-propelled at the interface. And that is fantastic. For example, if you want to clean something which is at the interface, you can use these kind of artificial active surfactants. And also, one step further is why not active polymers? Then you have block copolymers. You have one block with clockwise spinners, another block with anti-clockwise spinners. You can link many of them. You have a flexible polymer chain. And so, believe it or not, you have many interesting new structures, which we also called, one of the structure we called rotel, since that is a portmanteau of rotation and micelle, and rotel is also an Italian pasta, if you Google that. So it's a little wheel. Rotel is a little thing. It's a little wheel which resembles the micelle. A micelle is also an object which has surfactant on its cover, on its surface. Okay, so that's basically what I wanted to convey. So self-propelled colloidal Janus particles show fascinating single and collective phenomena, and dry inertial active matter is also full of new effects, and we are just at the beginning of exploring everything. I thank you for your attention, and here I give credit to some of my collaborators. Thank you very much.
Thank you, Hartmut, for the beautiful talk. Are there questions?
Thank you, Hartmut. So now I have a question about the MIPS separation. And in the movie that you showed for the experimental, for the experiment searching for MIPS, in the experiment was observed that they form like a large, only one large cluster, or
This one?
Yes, for example, this one.
Oh, no, it was,
so because
it was close to one large cluster.
Okay,
Yeah.
they form?
If
For
you-
long times?
This is only one movie. So if you increase the Peckley more, you get a larger cluster.
Okay.
And this is also a cutout of the system. The system is much larger. The simulation is the system size, but in the experiment it is larger. So, yeah.
Okay. Yeah.
But ideally, there should be a point where you get one big cluster,
cluster.
after a very long time.
Yeah. Okay, thank you. And the second question is about the inertial microswimmers. So I was wondering, you mentioned briefly why the diffusion coefficient that doesn't depend on the third temporal. Yeah. Do you have an idea why is this? Or?
Yeah, it's. I have an argument, but just an intuitive argument, since what matters is persistence. And by the mass, you cannot change the persistence. By the moment of inertia, you change the persistence. That is the only argument I have.
It seems that the only rotational diffusion, again, is like playing the key role
Yes, yes.
on the dynamics.
And that's, you know, in many ABP models, you just neglect the translational fluctuations. It's a good model still, since they are not so much important.
Yeah.
But you can fine-tune the persistence length and the persistence time by the rotational inertia. So you have an additional knob which you can change. And in the granular systems here, we really did that. So we prepared. These are different particles, and they have a different moment of inertia. So we glued some mass here. It's a mass ring. This is a light particle. This is a heavy particle, not only in terms of mass, but also in terms of moment of inertia. So you can vary that.
Good. Thank you.
Thanks for the lecture. There is some example of MIPS in living systems in nature.
What in? MIPS
There is some example of MIPS in living systems in nature. Living systems in nature. Some example of MIPS.
Okay, I think in cells you can see such a segregation as well. Yeah? In highly confluent tissues, you can see that. Let me see. There must be more, but it doesn't come to my mind. Yeah?
There is a paper by Peruani where they turn off quorum sensing between bacteria and they still do MIPS.
Yes.
Yeah.
Bacteria. Yeah.
Okay, thank you for the very nice talk. And two very quick questions, right? In the case of phase separations, you show like velocity distribution.
Yeah.
Are those Maxwell-like distribution or like a heavy-tailed distribution?
Okay. We haven't explored that, but I think it's Gaussian. I mean, for the theory, it is Gaussian. There's no heavy tails. And for the experiment, you simply have no data in the tails. Mm-hmm. So that would be the answer. So no Levy, unfortunately, maybe.
Okay. And the other one, you mentioned like cells adhesion, something like that, and you show only like the Weeks Chandler potential, like just. Have you explored any other potentials to maybe mimic like brain cells or
well,
tissue?
I mean, if you use other soft repulsive potentials, you get the same. We use Yukawa, by the way, a lot. Okay. Yukawa potentials. I mean, for charge systems. If you get Lennard-Jones, we did that also. That's the PRL which was published this year. If you have attractions, it's completely different. And then you get something flocking-like behavior and also flocking-like polarization is then long-ranged, if you like. So what I was saying here was just for repulsive systems.
I have a question about MIPS as well. You said that the reason why the mechanism behind is because of the persistent length of the direction of the particles, right?
Yeah.
But if I think about normal granular media without activity, they also display this type of phases, isn't it? Because the mechanism would be different, but they would get together and they would lose energy and they would not be able to go out.
Yeah, but the persistence length would be 0, since they forget immediately where they came from. And you need attractions to keep them together. If you have no attractions, you just...
But in granular media, we do observe those type of aggregations, right?
In random media?
Yeah, normal one without any attraction.
But then you have a landscape of an external potential that has, say, shallow minima and good minima, then the particles go there, and then it's different physics. But okay. I was only talking about bulk, so no external potentials.
Okay. So
but that's a good point, yeah? So.
I said granular media. He says that...
Okay. Granular systems.
Yeah.
Okay. Now I got the point. So granular systems can cluster, yes.
Yeah.
But they lose energy since they have friction collisions. Right. So they're just getting stuck, and then they're getting slower. But it's a good question. So the important point here, we have a Hamiltonian interaction. There's no friction. Otherwise, you'd say it's like a granular clustering, which exists. But for granular clustering, there are no, say, conservative forces, which we have. So it is surprising. So thank you. It was a very good point. Yeah.
Are there more questions? Oh, Lucas.
Thank you very much for the nice talk. I didn't quite understand that the part that you talked about, the cooling of the cluster. The cooling of the cluster is cooler than the media.
Oh yeah.
Why is this happen? What is this mechanism behind
Good
this?
question, since this brings me to an additional slide. So, yeah. I mean, this is a low density phase, and there you accelerate until you achieve the, say, self-propulsion speed. There's no other particle, there's no obstacle. which means high temperature. Now, in the dense phase here, you're in a cage. And you try to accelerate. But then there comes already the first collision. And it's bounced back. You really bounce back. It's like a ball. Yeah? You self-propel it by gravity, but it bounces back. And this keeps you, on average, keeps you cooler. Since the correlation of F with velocity again, which is the power, is smaller. So the idea is there are so many collisions that you have no time to get accelerated.
So it's like a definition of temperature based on the velocity of the particles.
Yes, yes. This is the kinetic temperature. That's a very important definition here. Okay. You are just stuck. You are just slower.
Thank you very much.
More questions? If not, let's thank Hartmut again and have a coffee break.